Hello everyone, welcome to today's lecture on the 8086 microprocessor. In this video, we will study an important architectural concept called memory banking. This concept is fundamental to understand how the 8086 access the memory. Designing memory interfaces and explaining why a 16-bit processor behaves the way it does. So our goal today is not only to know what memory banking is, but to clearly understand why it exists and how it works. Before defining memory banking, let us recall two basic facts. The 8086 is a 16-bit processor, meaning it can process 16 bits of data at a time. Each memory location stores exactly 1 byte, that is 8 bits. This immediately creates a mismatch. The processor wants 16 bits in one cycle, but memory provides only 8 bits per address. This mismatch is the root cause for memory banking. A natural question arises. Why not make each memory 16-bit wide? Although this sounds simple, it leads to serious inefficiency. Consider a 8-bit value like 34H. Only 8 bits are actually required. The remaining 8 bits in memory location remains unused. Since most program deals with large amount of 8-bit data, that is characters, flags, small numbers, this approach would waste a huge amount of memory. Therefore, memory designers follow an important rule. One memory location should be as small as possible. In practice, the smallest efficient unit is 1 byte. That is why one memory location always stores 1 byte. Since we cannot increase the size of memory location, we adapt a different solution. Instead of using a single memory chip, the 8086 uses two memory banks. Each banks provide 8 bits. Both banks together provide 16 bits. By accessing both the banks simultaneously, the processor can read or write 16 bits in one cycle without increasing memory location size. This technique is called memory banking. Let us discuss on the organization of 8086 microprocessor banks. The total memory of the 8086 is 1 MB, which is divided as follows. The lower or even bank of 512 KB and higher or odd bank of 512 KB. The address distribution is even address stored in the lower bank, odd address stored in the higher bank. For example, 000H is stored in lower bank, address 0001 is stored in higher bank. Similarly, 00002 is stored in lower bank, 4 zeros followed by 3 is stored in higher bank. Thus, consecutive memory locations always lies in different banks. The division is not based on address range but on address parity. Now let us see how data alignment affects memory access. There are two types of data. One is of aligned and misaligned. Aligned data are a 16-bit data is to be aligned if it starts at even address. Example, data stored at 0002H and 0003H or of aligned data. In this case, one byte is in the lower bank and one byte is in the higher bank. Both banks are activated simultaneously. So the processor reads or writes the entire 16-bit data in one cycle. Now let me tell you about the misaligned data. A 16-bit data is said to be misaligned if it starts at odd address. Example, data stored at 0003H and 0004H are misaligned data. Here, the processor cannot activate both the banks together for these two addresses. Therefore, the access must occur in two separate cycles. Misaligned data is valid, but it is slower. Why misaligned data requires two cycles? Memory bank selection depends on higher address line A19 to A1. Bank selection signals when aligned data is accessed, that is eliminate A0. You just eliminate this A0. If we eliminate this A0, then what happens? Both the banks, that is the location 0 and location 1, both the banks having similar fashion of binary number, or we can say that they are having same address. So parallel access is possible now. So we can take it. We can take the data simultaneously. For a misaligned data, if we take that the address 1 and 2, that is location 1 and 2, here the binary fashion is of completely different. They are of completely misaligned, right? So we can't take the 16-bit data at one instant of time. The 8086 uses two signals to control the memory bank. A0, that is equal to 0, which selects the lower bank. When A0 is equal to 1, lower bank is not selected. BHE bar, that is bus high enable, active low signal. When BHE is equal to 0, then higher banks are selected. When BHE1 is 1, higher bank is not selected. Using A0 and BHE together, the processor decides which bank or bank is activated or not. The processor generates A0 and BHE based on the instruction written on the program. So the instruction determines whether the data is 8-bit or 16-bit, whether access is aligned or misaligned, and whether one or two cycles are required. The same concept extends to modern systems. The 16-bit processor has two banks, that is our 8086 has two banks. 32-bit processor has 4 banks. 64-bit processor has 8 banks. That is why modern RAM module contains multiple memory chips working in parallel. Let us summarize the thing what we have discussed in this video. The memory banking solves the mismatch between processor width and memory width. It allows faster access without wasting memory. 8086 uses two banks, even and odd. Aligned data is faster and misaligned data is slow comparing to that of aligned data. A0 and BHE controls bank selection. Memory banking is not a topic to memorize. It is a concept to understand logically. Once this concept is clear, topics such as memory interfacing, address decoding, and instruction execution timing becomes much easier. Thank you for watching and happy learning.